So today we're going to talk about more consequences of completeness. So let's take a look at our first theorem. Okay, so our first theorem says something like this. So before we read the actual statement, I'll tell you the idea of it. Basically, it says if we zoom in to our real line, so we have some closed interval here, and then we have a smaller closed interval inside of it, and then a smaller closed interval inside of that, and smaller, and we keep going down and down. We're always going to find something down in there, at the bottom of that intersection, quote unquote. So the further we zoom into the real line, we're always going to at least find something. We never get the empty set. And this is intuitively, this calls to the idea that the real numbers don't have any holes in them. Okay, so the further you zoom in, you're not going to see some blank space there. There's always going to be something in there. So this is going to be a consequence of completeness. And so that should give you some sense in which the completeness axiom is going to tell us that the real numbers don't have holes in it. Okay, so we just say this precisely for each natural number. We have a closed interval. And the intervals really do have to be closed. You can't change this to open or half open intervals, which I think I'll probably assign a homework exercise about, or you can think about for yourself. Try to find a counterexample to this where you have open intervals, such that each successive interval is inside the previous one. Okay, so we're always sort of getting smaller intervals. Then the intersection of all of these sets is not the empty set. Okay, so and just point out also that this intersection doesn't have to be getting strictly smaller. We could, you could stabilize after some point, right? I mean, it might be the case that all of these sets are just the same closed set, for example. So you might just have a full closed interval. But in any case, that's what the theorem says. So let's see how we might prove this. So we would like to use the completeness property, the completeness axiom, which says that if we have a set that's bounded above, then it has a least upper bound. So kind of looking at this figure here, what kind of set do we see that might be bounded above, and then looking at the least upper bound might be helpful? Well, in this figure, we have the A's, the left endpoints of the closed intervals that are sort of marching rightward, right? So these are going to be bounded above, and they seem to be sort of coming to some point potentially. They're going to be, sort of limiting to some point in some sense, which of course we'll be making precise in this course. So there should be a least upper bounds to these A's somewhere in here, and we should be able to use that to produce, so that least upper bound should be the thing that's in this intersection, at least something that's in this intersection. So that's the basic idea. So I think it should be apparent from the figure, and it's not hard to show at all. You should try it if you're a bit skeptical, that any one of these A's is less than any one of the B's. Right? So just so note that K is less than or equal to BL for any K and L in the natural numbers. So in particular, AK is less than or equal to, say, B1 for all K. And what this tells us is that if we consider the set capital A of all of our A's, then that set is bounded above. Okay, so thus the set A, which is the set of all of the AK's, AK, where K is a natural number, is bounded above. So by completeness, of R, A has a least upper bound, and that is, let's say, L, which is the supremum of A. Now what we need to show, what we're trying to say is that this L is in the intersection of all of these IN sets, all the intervals, and so we just need to say that it's in each of the intervals. Okay, so we need to show that L is in IN for each n. And that is, so to be in that interval just means that it's bigger than or equal to AN and less than or equal to BN. So that is that AN is less than or equal to L is less than or equal to BN for each n. Okay, well, L bigger than or equal to AN is trivial because L is an upper bound for the set A, which is just all of the little a's, right? So the inequality, or well, maybe I'll say it this way. Since L is an upper bound for A, AN less than or equal to L is automatic. And sort of the usual thing to do to show an inequality like this is to show that the negation of this inequality can't occur. Okay, so we rule out Bn less than L by contradiction. So we'll rule out Bn less than L by contradiction. So assume that Bn is indeed less than L. Well, what's the problem with that? Well, you can think about it here. I mean, you have these Bn's here. If you imagine L is to the right of one of those B's, well, then that Bn, right? So then this Bn, that Bn is to the right of all of the A's, right? So that makes Bn an upper bound for the A's, which is smaller than L, but L is supposed to be the least upper bound. Right, so we noted in the beginning here, all of the B's are at least as big as all of the A's. So this sort of just immediately from this and this, we get a contradiction. So since, as noted above, A k is less than or equal to Bn for all k, Bn is an upper bound for A. But then this contradicts since, or I guess I should say, and since Bn is less than L, this contradicts the fact that L is the least upper bound. So we're done. All right, because we showed that L here is in each IN, and therefore it's in the intersection. So we have a non-empty intersection. So a direct corollary of this proposition, corollary, R is still uncountable. Okay, so this is a different proof that R is uncountable. And the advantage of this one is that it really does, right, our proof here just came from the axioms of the real numbers. This corollary is just going to depend on this. It doesn't depend on the model of the real numbers as decimals. It really just follows directly from the axioms. So you can see, I mean, and it's a much cleaner proof. So you get this, I don't know, increased clarity, conceptual clarity by focusing on the axioms. At least I think so. So of course the proof is going to be by contradiction. So by contradiction, suppose R is countable. That is to say, we have a list, a comprehensive list of all of the elements in the reals. So what we're going to do is show that in this case we can get a contradiction to the previous theorem. Okay, so the strategy is to contradict the nested interval property. And the idea is pretty simple. What we want to do is construct some intersection, right, a bunch of intervals, and then look at the intersection. And the idea is this, that if, say, if xi, and if one of the x's is going to be in this infinite intersection, then it has to be in every single one of these intervals, right? And so all I have to do to get xi, this arbitrary xi not in this intersection, is to ensure that it's not in a single interval. Okay, so for example, to ensure that x1 is not in this infinite intersection, all I have to do is make sure that x1 is not in I1. If x1 is not in I1, it's not in the intersection. And then all I have to do to ensure that x2 is not in this infinite intersection is to ensure that x2 is not in I2, right? So for each one of these countable intervals here, right, I just sort of pair the interval with one of these numbers, and I say, so I1 is just not going to have x1 in it, and I2 is not going to have x2 in it. And so we'll show how to construct intervals that do that. And as long as I can do that, then the intersection is going to be empty because it's not going to contain each one of the points on this list. So what we do is we will construct in such that xn is not in in. If this is the case, then xn is not in the intersection of all of the INs, and that holds for each n, for all n. And that means, which means since the xn's are all the elements of R, which means there is no real number in that infinite intersection, i.e. that infinite intersection is equal to the empty set. Okay, so what's this? This gives us clearly our goal. We just need to construct this sequence of intervals so that xn is not in in. If we do that, we're done. Okay, so to do this, so to construct intervals such that xn is not in in, we proceed by induction. Okay, so I'll show you how to do it for x1. That'll be easy, and then I'll show you how to do it inductively. If you've already constructed it done it for a bunch of intervals, how to do it for the next one. Define for the base case just define I1, which is A1, B1, to be any interval that doesn't intersect with x1. So say like x1 plus 1, comma x1 plus 2, something like that. So x1 plus 1, x1 plus 2. Okay. And then clearly x1 is not in that interval. So now suppose that we've done it for I1 through IN. So now suppose I1 through IN have been constructed such that xi is not an element of I sub little I. And I just realized that I didn't state something explicitly, which I should have. I was just kind of thinking it in my head without actually saying it. What we need here is we need to construct our intervals to satisfy the hypotheses of the NIP, right? So we need our intervals to be nested. So it's the nested intervals property. So what we need is, I need to add in here and n, or well, in plus 1 is contained in in. Okay, and then what we would have, right, so if we do this and then we construct this intersection which is empty, then this would contradict the NIP. So this contradicts the nested interval property. Okay, so when we're doing this inductive construction, we're going to suppose that that all these intervals are nested appropriately. So sorry, I didn't want to go back and erase everything. I could just quickly insert this. Having constructed such that xi is not in I sub I for I from 1 to n, and I sub I is contained in I sub I plus 1, or contains I sub I plus 1. Okay, so the basic idea is this: if we have, if this is in, the last interval we constructed, there's going to be two cases. So in plus 1, if in plus, or sorry, if x n plus 1 is outside of this interval, then we can just take in plus 1 to be in. Okay, so we either have this, either that's the case, or your xn plus 1 could be in here. And then if xn plus 1 is in there, then all we have to do is just show how to construct an interval inside of in, which avoids that xn plus 1. And one way to do that would be to say just take the midpoint of an and xn plus 1 here and then use that interval. So we might do something like take the midpoint between an and xn plus 1, which is right here, and then consider that closed interval. The only problem with that is if xn plus 1 just happens to be an, and then the midpoint is an, so that could create a problem. But in that case, then, so if xn plus 1 is just an, then we can just take the midpoint of the whole interval, and so we'll just do something special for that. So if xn plus 1 happens to be here, then we can just take the midpoint of xn plus 1, which is just an and bn, in other words, the midpoint here, and then we'll use this as our subinterval. Okay, so just some simple construction using midpoints to appropriately avoid xn plus 1. Okay, so I've outlined those different scenarios in the figure there, and then I'll just write this down accordingly. Okay, so to begin with, it's either the case that xn plus 1 is not in in, or xn plus 1 is in in. If the former, just set in equals in plus 1, and clearly then xn plus 1 is not in in plus 1 because in plus 1 is in, and in plus 1 is contained in because they're equal. Okay, in the latter case, either xn plus 1 is not equal to an, or xn plus 1 does equal an. If xn plus 1 doesn't equal an, then we're just going to set in plus 1 to be equal to the interval from an to the midpoint between an and xn plus 1. So an plus xn plus 1 over 2. And it's easy to check. it's easy to check that an plus xn plus 1 over 2 is less than xn plus 1. So that means, so xn plus 1 is not in in plus 1, and that an plus xn plus 1 over 2 is less than or equal to bn, so that in plus 1 is contained in in. Okay, so that completes the induction step in that case. And then finally, if xn plus 1 does equal an, set in plus 1 equal to an plus bn over 2, comma, bn. And similarly, we can check. Similarly, one can check, just simple thing with inequalities, that xn plus 1 is not in in plus 1, and in plus 1 is indeed contained in in. Okay, so this completes the proof. Okay, so that completes our inductive construction, and we already explained above why the inductive construction will contradict the nested interval property, and so the conclusion follows. Okay, to motivate the next theorem that follows from completeness, I want to consider an example. So we'll look at the set of 1 over n, where n is a natural number. Okay, so this is the set. So this is the inf of the set 1, 1/2, 1/3, 1/4, 1/5, etc. Right, so it's clearly tending down to 0, and so the infimum, that would be the greatest lower bound. Right, 0 is going to be a lower bound, and it's pretty clear intuitively that 0 should be the greatest lower bound, or the infimum of this set. But let's think about how we would prove this. Okay, so the claim is that this inf, I don't know, just call this set A, is that the infimum of A is equal to 0. And so let's ask ourselves why. Let's see if we can prove this. So clearly 0 is less than everything in A. Okay, so it is a lower bound. So is it the greatest lower bound? Okay, so that's the first point about lower bounds. Or that's the first part about infimums. They have to be a lower bound. So is it the greatest lower bound? Well, take some other lower bound. So let V be some other lower bound of A. What we have to show, so we want to show that 0 is the greatest lower bound, so we want to show that 0 is bigger than or equal to this V. So we want to show that V is less than or equal to 0, which, as usual, we do by ruling out 0 less than V. Okay, so we want to rule out the possibility that there's some lower bound of this set which is somehow bigger than 0. So in other words, we need to rule out the possibility of there being some V in R such that 0 is less than V, but V is less than or equal to 1 over n for all n. Or equivalently, just by inverting this here, the existence of a real number r such that, so r is going to be 1 over v. So such that 0 is less than r, or excuse me, 0 is less than n is less than or equal to r. Okay, so we inverted this inequality and it switched them, and so n comes over here, 1 over v goes over there, and we'll call that r. Okay, so it might seem absurd to you to have to prove this, to have to even consider this. I mean, some real number which is smaller than all the 1 over n's, or in other words, some real number which is bigger than or equal to all the natural numbers, and a real number that's bigger than or equal to all the natural numbers. Natural numbers sort of go out, as far as you can, right? There can't be a real number bigger than that, right? Well, we have to prove it. And it's not in the axioms, right? It doesn't, there's no axiom that says that this can't be a possibility. So we have to rule it out somehow. And in fact, it follows from the completeness axiom of the real numbers. It doesn't follow from the other axioms because there are ordered fields where this can happen. Okay, so there are ordered fields where you have elements that are bigger than or equal to all of the natural numbers. In other words, this natural number is just 1 plus 1, n times. So you can have ordered fields where there are elements that are bigger than or equal to all of those natural numbers. Okay, so here's my official note about this. So the existence of a real number bigger than or equal to all of the natural numbers is not immediate from the axioms. Okay, there's no axiom that says that this can't happen. And in fact, it doesn't follow from axioms 1 to 13. Okay, so we really need the completeness axiom number 14, and there are ordered fields. There's explicit examples. The one I know off the top of my head is called the hyperreal numbers, which you might want to look into on Wikipedia or something, where it fails. Okay, so there are ordered fields where you have elements that are bigger than or equal to all of the natural numbers. So basically, these hyperreal numbers are basically the reals, but added with infinitesimal and infinite elements added. So you have sort of infinite elements of the hyperreal numbers, which are bigger than or equal to all of the naturals, and perfectly logically well defined. You can manipulate them and do arithmetic with them. So if we want to know this for sure, we need to see how it follows from the completeness axiom. Okay, so that's essentially what the next proposition is doing. Okay, so our proposition, which is often referred to as the Archimedean property, especially this first part here, that for any real number, there's got to be a natural number which is bigger than it. Okay, so the natural numbers keep on going and exceed any given real number. There's no real number upper bound to the natural numbers. And another way to basically say the same thing is that for any real number and positive real number, you can take some natural number such that n times x is bigger than y. So in other words, basically, no matter how small this x is here, I can always duplicate it a number of times. So if you're thinking about these as like a stick of length x, no matter how small that stick is, I can duplicate it a number of times so that it exceeds any given length. Okay, so that's sort of the way to think about that. And these two are just equivalent. Also equivalent is that for any y greater than 0, there is a natural number such that 1 over n is less than y. Okay, so the 1 over n's get arbitrarily small. That is, there's no real number which is bigger than 0, but somehow less than all of the 1 over n's. And then we have number 4 here, which says that for any real number, we can put that real number between two consecutive integers. Okay. So all of this, right, just confirming from the axioms what things we already know, right? So the axioms really are reflecting the structure of the real numbers that we've come to understand over time. So in other words, the way that we commonly conceive of the real numbers, thinking about them as decimals, and as this picture along the real line. I mean, those things aren't illusions. They really do follow, they really are key to the structure and the properties of the real numbers. Okay, so as to the proof here, let's look at 1. So we're going to prove this by contradiction, show that so if there is an x which is bigger than or equal to all of the natural numbers, then the natural numbers have an upper bound, so they have a least upper bound, and we'll see how that plays out. So suppose for the sake of contradiction, that there's some x, so that the natural numbers are bounded above by some x. So for some x. Then by completeness, there's a least upper bound. There is a least upper bound L, which is equal to the sup of the naturals. And so the reason this is crazy goes back to the old grade school thing. Why is there no largest number? Well, because you can always, if there were a largest number, you can always just add 1 to it, and that's going to be bigger, right? So what we have here is that you have this L, which is supposed to be the least upper bound of the real numbers, or of the natural numbers, excuse me. So you have this, so let me draw it. So you have this L here, and then all of the natural numbers are supposed to be coming up to that point, right? So you have the natural numbers, and there's some weird situation, like, I don't know, like somehow the naturals are like compressing or something. They're sort of getting close to that L, but actually never get bigger than it. But that doesn't make any sense, because if you walk back by 1 here, so you do L minus 1, say, so you have L minus 1 here. Well, we know that so you might remember last time that the last proposition we talked about, if you take your least upper bound for a set and you subtract any amount, some elements of that set have to be in this interval here, right? So there have to be natural numbers in here, but then we can just add 1 to that natural number, and then we have L minus 1 less than our natural number, but then we add 1, right? Then we get L is less than that natural number plus 1. And so we find that there is indeed a natural number, which is that whatever that thing is plus 1, which is bigger than L. Okay, so that's the whole proof. We just look at our least upper bound and we subtract 1 off of it. There's got to be a natural number bigger than that. Okay, so then we know that there must be some n. There must be an n in n such that n is in the interval L minus 1 comma L. Okay, we could do this with any epsilon, any positive epsilon, but we can just take 1 here for simplicity. So there's an n in there, thus L minus 1 is less than n, which is equivalent to saying that L is less than n plus 1. But n plus 1 is a natural number. And so, well, then L was supposed to be bigger than or equal to, it's an upper bound, right, for the natural numbers, but now we see that it's not an upper bound for the natural numbers. That's a contradiction. So n plus 1 is a natural number. Or I guess I could just say which contradicts the fact that the natural numbers are supposed to be bounded above by L. And so that's that. Okay, so for 2, 2 is very simple. You just consider, so use 1 with y over x, right? So then we get y over x less than n for some n, which is equivalent to y is less than n times x. Okay, no brainer there. And 3 is almost as simple. So if we have y here, then just consider 1 over y. So use 1 with, right, because this thing we're aiming at is just equivalent to saying 1 over y is less than n. So use 1 with x equals 1 over y. We get n bigger than 1 over y, which is equivalent to y is bigger than 1 over n. Okay, and then we just have to do 4. Okay, sorry, but I actually decided to change things up just a little bit. I've added a different 4, and now our previous 4 is 5. So this new 4 is saying that for any x in the real numbers, there's an integer which is less than x. Okay, and then for any, and then the previous 4 is now 5, that we can squeeze any real number between 2 consecutive integers. Okay, but it's just cleaner to do this one first. So this essentially, well, anyway, we'll see how that goes. So 4 here, for any x in R, there's an integer such that n is less than x. Well, we just have to consider, so use 1 with negative x. So we get negative x is less than n, and that is equivalent to x is bigger than negative n, and negative n is an integer. All right, so, or well, I guess I should say m, let's say m, then set negative m equal to n, which is an integer. Okay, and then we move to 5. And 5 is very much like the argument in 1 again. So basically what we want here is we want the integer which comes closest to x from below. Okay, so what we want to do is we'll consider all of the integers that are less than x, and then use the least upper bound property to try to figure out what that n is. Okay, so what we'll do is consider the set A, which is all of the n in Z, such that n is less than or equal to x. Okay, and this is not empty by the it's not empty by the number 4. Okay, so we're not considering something trivial here. And obviously it's bounded above by x, right? So obviously A is bounded above by x, so let L be the least upper bound, which is the sup of A. So as in 1, then there is an n which is in A, so there's some integer such that n is in the interval from L minus 1 to L. And now from this, what we have is L minus 1 is less than L, or n is less than or equal to L, and L is the least upper bound of A, whereas x is an upper bound for A. So that means that L is less than or equal to x. And so what we see is, remember what we want is for, we want x to be less than or equal to this n, and then less than n plus 1. Right, this is what we want. So we automatically have x is bigger than or equal to n, and then we have to say that x is less than n plus 1. But you see, n plus 1, what we can get is that L is less than n plus 1, right? And what this means is that n plus 1 is not in the set A. Right? Because if n plus 1 were in the set A, well, L is an upper bound for A. So L would have to be bigger than or equal to n plus 1, which it's not. So that means n plus 1, the only possibility is that it's not in A. And if it's not in A, then that means that n plus 1 must exceed x, right? Because if n plus 1 didn't exceed x, then by definition it would be in A. Okay, so then this implies here that x is less than n plus 1. So that's the remainder of the argument there. So to write that down, then n is less than or equal to L, which is less than or equal to x, using that that L is equal to the sup of A in the second inequality there, in the second inequality. And also, L minus 1 is less than n, or equivalently, L is less than n plus 1, which implies that n plus 1 is not in A, since L is bigger than or equal to everything in A. And now, by definition of A, then n plus 1 must be bigger than x. So x is less than n plus 1. Thus, n is less than or equal to x is less than n plus 1 as desired. And just a word about this proposition. The first part here, so the first part is in the text, and the third part is in the text. The second part I threw in for fun, and the fourth and the fifth part, really, Abbott ends up using number 5 in the proof of the next theorem, but he doesn't really acknowledge that he's doing anything non-trivial. So I think he might have somewhat erred there logically. So I wanted to close that gap, and you can find this number 5 in the Gowan text also. Also, as a postscript to number 5 here, you might find it a fun exercise to show that this n has to be unique. So there can't be an m and an n that are different, such that this is true. So you can just mess around with some inequalities. It's not hard to do. So now that we know how the natural numbers and integers sit in the real numbers, we can deduce how the rational numbers sit in the real numbers, confirming our existing intuition, which is that if you have any two real numbers, one less than the other, then you're always going to be able to find a rational between those two real numbers. Okay, so in some sense, the rationals are going to be, in this sense, the rational numbers are dense in the real numbers, right? No matter, you're always going to see, there's never any interval in the real numbers that doesn't have a rational number in it. Okay, so the rational numbers are everywhere. Okay, so the basic idea of how to do this is this rational number here is p over q, where p is an integer and q is a natural number. So we're trying to find these p and q, okay? And we want the p and q to satisfy x less than p over q less than y. And we're going to make this a statement about just the integers by just multiplying through by q here. So qx less than p less than qy. So in other words, what we're doing is we're looking for q such that there's an integer p in the interval between qx and qy. Okay, so we're trying to identify, so the first thing to do is to try to identify this q. We want qx, the interval qx, qy to have an integer in it, right? So we need qx, qy to have an integer in it. And so we can picture this qx, qy right? When is an integer going to be guaranteed to fall in an interval like this? Well, intuitively, we just need the length of this interval to be bigger than 1. Right? So basically what we want, so intuitively we want qy minus qx to be bigger than 1. And we can just rearrange this to say that q is bigger than 1 over y minus x. Okay, and of course we can do this by the Archimedean property. So that's the starting point, is to consider 1 over y minus x. You get your q, and then you have to argue that there's going to be an integer in that interval. So that's what we're going to do. That's the plan. Okay, so the proof is right. So what we do is consider, so by the Archimedean property, there is a q in the natural numbers such that 1 over y minus x is less than q. So thus, just rearranging this, right, we have that 1 is less than q times y minus q times x, or equivalently that qx plus 1 is less than qy. Okay, and so the basic intuition, and just to sort of reinforce again, we have qx, qy, we have qx plus 1, right, so this is qx plus 1, that's less than qy. So we're going to find p. So intuitively, p is going to be 1 more than the integer which is closest to qx, closest to and less than qx. So remember, we know that qx is going to be bigger than or equal to some integer m, right, and less than m plus 1. So this m is going to be like somewhere here, and if we add 1 to that m, that's going to fall up here, right? So m plus 1, this is going to be our p, which equals m plus 1. And since m is less than qx, our p is going to be less than qx plus 1, and that's going to be less than qy. So that's going to mean that p falls in this interval between qx and qy. So then we let p in, or not p, let's say let m in z be such that m is less than or equal to qx, which is less than m plus 1. Okay, so by the previous proposition. So by our previous proposition. And define p to be equal to m plus 1. So then p is bigger than qx. We just have to see that p is less than qy, right? And so then p, which is equal to m plus 1, m is less than or equal to qx. Right, so we have qx plus 1, and qx plus 1 is less than qy. So that's less than qy, and therefore we have we have qx less than m plus 1, which is by definition p, and we just showed that p is less than qy, and q is a natural number, so we can just divide that. We get, by that q, we get x is less than p over q, which is less than y. So then setting p over q equal to r, that's a rational number, completes the proof. And our last theorem, which is a consequence of completeness, is the existence of square roots. Okay, so we can show that if we have a positive real number, then there is another real number which squares to that real number, that given real number x. Okay, and so the proof is to consider, consider the set of all of the real numbers which square to less than x. Okay, so consider A, which is the set of y in R such that y squared is less than x. Okay, and note this is non-empty, so A is not the empty set since, for example, 0 is in A. I guess maybe I should own up to this. I think when I was stating the completeness property of the real numbers, I didn't specify non-empty subset of the reals. So when you're applying the completeness property, it applies to non-empty subsets of the real numbers because the empty set is vacuously bounded above. But we don't really want to say the empty set has a least upper bound. Okay, so we're not considering the empty set when we're talking about bounded subsets of the real numbers that are bounded from above. So mea culpa, I apologize for that. Technically, you should be checking that your sets are not empty before you apply the completeness axiom. Okay, so our set is not empty, and we need to show that our set is bounded. So we claim that A is bounded above So the basic idea of this claim is that each of these y's, so you want to bound the y's, and what we have is a bound on the y squareds. So y squared is less than x. We know that x is less than some natural number, say, right? And then we can say that n is less than n squared. So 1, or at least less than or equal to n squared. So 1 is less than or equal to n, whatever this n is, and multiplying that through by n, since n is greater than 0, gives you that, right? So we know that this is less than or equal to n squared. Right. So that tells us that y squared is less than n squared for some natural number n, and then we claim that that implies that. So this is going to imply that y is less than n. And there's basically two cases: either y is less than 0, and then that's automatically less than n, or y is bigger than 0. And if y is bigger than 0, then what you use is the fact that this is equivalent to 0 less than n squared minus y squared, and then you can factor this, right? N minus y and n plus y. And n plus y is, each of these are positive, right? So you have a positive number here, but the product is positive, so that means that n minus y must be positive, which is the same thing as n bigger than y. Okay, so that implies that all of our y's are going to be bounded by whatever that n is. So let's just write that down. So we know that we can find, by the Archimedean property, we can find n in the natural numbers such that n is bigger than this x, such that x is less than n, and n is less than or equal to n squared, right? So thus, any y in A satisfies y is less than, that y squared is less than n squared. And so we claim that y is less than n. So either y is less than or equal to 0, in which case y is less than or equal to 0, and 0 is automatically less than n for any natural number, or y is greater than 0. So in the latter case, this latter case, we have that n squared minus y squared, let me say this way, 0 is less than n squared minus y squared, which is less than n minus y times n plus y. And that means we have a product which is bigger than 0, and n plus y is greater than 0. In this latter case, we have that inequality, but also n plus y greater than 0, since n is greater than 0 and y is greater than 0. So n minus y is greater than 0 also. That is, y is less than n. Okay, so we have an upper bound. So this set A is bounded above by n. Okay, so since it's bounded above, we can take the least upper bound of this set. And sort of clearly, intuitively, the least upper bound of this set should be something that squares to x. And so you're looking at all the things that square less than x, and if you get as close as possible to x with all of those things, that's going to square to x. So now we consider, so using completeness by completeness, A has an upper bound, has a least upper bound, Let's say L is equal to the supremum of A. Or, sorry, I think I called it alpha up there, so let's say alpha. So alpha equals the supremum of A. And then what we want to say is we will show that alpha squared equals x by ruling out alpha squared bigger than x and alpha squared less than x. So we'll show alpha squared equals x by ruling out alpha squared less than x and alpha squared bigger than x. Okay, so we have essentially two cases. So suppose that alpha squared is less than x. Oh, whoops, I said less than and I wrote greater than. Alpha squared is less than x. So intuitively then alpha is too small, right? So, and what are the properties of alpha? So alpha is supposed to be an upper bound and it's supposed to be the least upper bound. So if our feeling is that alpha is too small, then intuitively that should contradict that it's an upper bound for A, right? That it's too small to be an upper bound for A. Okay, so we're going to see that this contradicts so we'll try to show, we're going to try to show that alpha can't be an upper bound for A in this case. Okay, and then with the other one, when alpha squared is bigger than x, we'll show that that contradicts it being the least upper bound. Oops, in this case. Okay, so what we'll do is to show that it can't be an upper bound for A, what we'll do is show that we can add a little bit to alpha and still make it be in A. Right? So basically we'll take this alpha, we'll add a little bit and show that that thing is in A, but if we add a little positive amount, and that's in A, that thing is going to be in A but bigger than alpha, right? So that would mean that alpha is no longer an upper bound for A. So consider alpha plus 1 over n, where n is in n, and we'll show how to choose n in a second, and we'll determine n in a bit. Okay, so what we want to do is show that we can pick this n so that alpha plus 1 over n is in A. Okay, so in order for alpha plus 1 over n to be in A, remember, A is all the stuff that squares to be less than x. Okay, so what we want here is, this is kind of like some scrap work, we want alpha plus 1 over n squared to be less than x, right? So we'll just square this. This is alpha squared plus 2 alpha over n plus 1 over n squared. And we would like for this to be less than x. And so what that means is we want this thing here. Remember, we're supposing alpha squared is less than x, so there is a gap between alpha squared and x, and we want this thing to be sort of smaller than that gap, right? So we want this thing to be less than x minus alpha squared. If this thing is less than x minus alpha squared, then alpha squared plus that thing is less than the sum of those, which is x, right? So we just need to consider x minus alpha squared and show that we can pick n so that this thing is less than that. And basically this is the Archimedean property. You want to pick n big enough so that some real number is less than n effectively. The annoying thing is this n squared here, but actually we can just do a simple little trick for that. So what we do is say 2 alpha over n plus 1 over n squared. That's less than or equal to 2 alpha over n plus 1 over n, right? Since n squared is bigger than or equal to n, so that's 2 alpha plus 1 over n, right? And if we can make this 2 alpha plus 1 over n less than, what did I say, x minus alpha squared, we should be good to go. And so that means we want n to be bigger than 2 alpha plus 1 over x minus alpha squared. Okay, and I guess I'll kind of rewrite the proof here. So I mean, this is the scrap work we have to do to determine n. So n here is, so consider alpha plus 1 over n, where n in n is such that 2 alpha plus 1 over x minus alpha squared is less than n by the Archimedean property. Okay, so we do a little scratch work trying to figure out how we can achieve our goal, and then we write it up nice. Okay, so let me just get rid of all this stuff. I think we have the thing we need. Then just do that computation again. Alpha plus 1 over n squared is alpha squared plus 2 alpha over n plus 1 over n squared. That's less than or equal to alpha squared plus 2 alpha over n plus 1 over n, which is equal to alpha squared plus 2 alpha plus 1 over n, and 2 alpha plus 1 over n is less than x minus alpha squared by this inequality. Okay, and so this is less than alpha squared plus x minus alpha squared, which is equal to x. So alpha plus 1 over n squared is less than x. So alpha plus 1 over n is in this set A, but alpha plus 1 over n is bigger than alpha, of course, and that contradicts the fact that alpha is the sup. So contradicting that alpha equals the sup of A. Okay, so thus it must be the case that x is less than or equal to alpha squared. Okay, so now we just have to rule out that alpha squared is strictly greater than x. All right, so suppose now that x is less than alpha squared. So intuitively then, alpha is too large. And alpha is supposed to be the least upper bound. So if our feeling is that alpha is too large to be the least upper bound, it must be that we can find an upper bound which is smaller. So in that vein, we're going to take our alpha and subtract a little bit off of it and try to show that this is still an upper bound. So the basic idea is to take your alpha minus 1 over n, show that the square of this is bigger than x. And then if the square of that is bigger than x, well, x is bigger than all of those y squareds, right? So again, we have this something squared is bigger than something else squared. That is going to imply that alpha minus 1 over n is bigger than all of the y's. So we have an upper bound for a, which is smaller than alpha, and that will contradict the least upper bound property. Okay, so we're going to consider alpha minus 1 over n for n in the natural numbers, and let's see what we want. So again, we want alpha minus 1 over n squared. That's alpha squared minus 2 alpha over n plus n 1 over n squared. And we want that to be bigger than x, right? So we want this to be bigger than x. And so that means we want 2 alpha over n minus 1 over n squared to be less than this positive number alpha squared minus x, right? We know that's positive by our assumption here. To do that, well, we can just do a similar thing to get rid of, actually we can do something simpler to get rid of the n squared in this case, right? We want this thing to be less than alpha squared minus x. Well, this thing is less than 2 alpha over n, right? So it suffices to make that less than alpha squared minus x, right? So we'll just choose our n. We'll need to choose our n large enough that it's bigger than 2 alpha over alpha squared minus x. And there's also something else a little bit subtle, which is that if we continue, right, so try to run through the rest of the argument with this choice of n, we're gonna have alpha minus 1 over n squared is bigger than x. X is bigger than all of the y squareds, right? So that's bigger than y squared. That's going to be the same as alpha minus 1 over n minus y times alpha minus 1 over n plus y greater than 0. Because what we're trying to say is that y is less than alpha minus 1 over n. Right, we're trying to say that this is an upper bound for all of these y's. So if we try to do the same argument we did before, then we had y when y is less than 0. Before we had an integer, and we were just able to say 0 is, or a natural number, that 0 is less than that natural number. But here we need to make sure that y is negative. We want it to be the case that this alpha minus 1 over n is positive. Right? So basically in this product over here, where the product of these two things is positive, we want to be ensured that this thing is positive by saying that y is positive and alpha minus 1 over n is positive. So one thing we need to know is that alpha minus 1 over n is positive. So in the negative case, when y is less than 0, 0 is less than alpha minus 1 over n, so we automatically get alpha minus 1 over n less than y. And in the case when y is positive, we use this factorization, then y is positive and alpha minus 1 over n is positive. So we also need to make sure that n is large enough that alpha minus 1 over n is greater than 0. Okay, that's the point. It's just a little technical detail, but it is important. So we're also going to need that alpha minus 1 over n is bigger than 0. In other words, n is bigger than 1 over alpha. Notice that actually to do this, so we can... In order to do this, in order to find an n such that alpha is bigger than 1 over n, we need to know that alpha is positive. But that is true because alpha squared has to be bigger than x, which is bigger than 0. Okay, so there's a bunch of little details we have to notice here to finish the argument. It's actually a little bit annoying, but nevertheless. So we'll consider. So actually, maybe in this first, maybe up here. So thus, x less than or equal to alpha squared. I'm going to note this implies that alpha is bigger than 0. Okay, so it's obviously the case that alpha is bigger than or equal to 0 because this set A that we defined contains 0 and alpha is the least upper bound. So alpha is an upper bound. So it has to be bigger than or equal to 0, but it can't be 0 now because we know that if it was 0, then you'd have x is less than or equal to 0, but x is supposed to be greater than 0. Okay, so we know that alpha is greater than 0, so we'll be able to find an n which is large enough that 1 over n is smaller than alpha, and we'll also be able to find an n which is big enough that it exceeds 2 alpha over alpha squared minus x. So we'll consider alpha minus 1 over n, where n is in n such that, so two things, let's see, I can get rid of that. So two things such that n is bigger than 2 alpha over alpha squared minus x. So that's less than n. And n is and such that 1 over n is less than alpha. Okay, and so we can do this because we consider this number here, we get some natural number which is bigger than it. We consider the n which is bigger than 1 over alpha, right? They might be two different n's, but then you just take the biggest one. Okay, so then we can get a single integer which works, single natural number which works. Okay, so then alpha minus 1 over n squared is alpha squared minus 2 alpha over n plus 1 over n squared. That is bigger than alpha squared minus 2 alpha over n. And 2 alpha over n is less than alpha squared minus x. So this is bigger than alpha squared minus x, which is equal to x. Okay, so alpha minus 1 over n squared is bigger than x. So therefore, for any y in A, alpha minus 1 over n squared is bigger than x, and x is bigger than y squared. So alpha minus 1 over n squared is bigger than y squared. And now we just need to say that alpha minus 1 over n is bigger than y. Okay, so this implies alpha minus 1 over n is bigger than y. For if y is less than 0, then y is less than 0, and we know that 0 is less than alpha minus 1 over n because we chose n such that alpha minus 1 over n is positive. And if y is bigger than 0, then this is just the same argument we made above, essentially. Then we have 0 is less than alpha minus 1 over n minus y times alpha minus 1 over n plus y, and alpha minus 1 over n and y are both greater than 0. So the right-hand multiplicand there is greater than 0, implying that the other one is also greater than 0. i.e., y is less than alpha minus 1 over n. Okay, so ultimately, so alpha minus 1 over n is an upper bound, so is an upper bound for the set A, but it's less than the least upper bound, alpha. So alpha minus 1 over n is an upper bound for A, and alpha minus 1 over n is less than alpha, which contradicting that alpha is equal to the sup of A. Okay, so therefore alpha squared equals x. Okay, so that's the existence of square roots. And you can run a very similar proof to show the existence of mth roots for any m. So if m, so generally, one can show that if you have x greater than 0 and m some natural number, and m is a natural number, then there is a alpha in R such that alpha to the m is equal to x. And it's the same general argument. You consider the set A of stuff which to the mth power is less than x. You show this is a non-empty bounded set. You consider its least upper bound, and then the key thing becomes the following identity. Let me give myself more room here. The am minus bm is equal to a minus b times a to the m minus 1 plus a to the m minus 2b plus a to the m minus 3b squared plus a b to the m minus 2 plus b to the m minus 1, which you can prove by induction on m. Basically, the a and the am minus 1 give you the am, and then the a and this term and the minus b and this term cancel. So you have like a to the m minus 1b right there, but then you have a to the m minus 1 minus b there. And so you get this this cancellation by pairs until you get to the point, so a times b m minus 1, that cancels with the previous term, which has a m b to the m minus 2, but then multiplied by minus b, and then the last thing is b times the m minus 1 with the minus sign gives you minus b to the m. Okay, so that's the basic identity that'll replace the difference of squares identity there. So that would be the key kind of thing. You can run through, it's the same outline of the argument, just a slight change in the technical details. Okay, so that concludes our lectures for the week on the real numbers. So next week we'll move on to things beyond the axioms for the real numbers, talking about basically sequences and limits and things of that nature. So more mainstream calculus kind of things. So these are the foundations. And we'll begin the real explorations next week.